Good evening. We'll begin lecture 11. In today's class, we would like to look at a couple of examples which highlight for us our understanding of the cellular system design using hexagonal cells and the tessellation. Also like to introduce you to looking at the aspects of signal quality. As we mentioned, cellular systems are interference limited. I'd like you to get a feel for what are some of the metrics that are used and how to interpret that. We move from designing a cellular system to understanding the capacity of a cellular system. That takes us into the discussion on trunking. Again, it's a term that probably some of you are familiar with, but we will define it, and associated with the trunking concept, the grade of service. We will spend a fair amount of time on a case study, a very interesting case study of a particular city, which is where 3 operators have deployed. Each of them has taken a different strategy. I would like you to analyze and think about what are the methods. To complete our basic understanding of the design of a cellular system, the last component will be the aspect of handoff, which is necessitated by the mobility of a user. As you move away from the coverage of one base station, move into the coverage of another base station, the mechanisms that must be in place for you to have a continuous call to be processed. So that is the plan for today's lecture. Again, I hope you have a copy of the outline of the course of the lecture, which was uploaded before the start. So the basic problem or the task of design is for us to look at the aspects of C over I estimation, and we can look at it in terms of the approximation that we have 1 over I naught d by r raised to the power n. N is our path loss exponent. Again, if you are talking about small cluster sizes, we saw that the impact of the distance between the interfering base station and the mobile is an important one. Sectoring, as we saw, gave us a ability to reduce the number of tier 1 interferers. Automatically that means C over I would go up. The drawback of sectoring was that you would have more handoffs, but more than the handoffs, you are actually going to affect yourself in terms of the trunking efficiency, as we will see in today's lecture. Other ways of improving C over I. One we said was frequency hopping. Basically, each of the users in the system are changing their frequency on using a pseudo-random frequency pattern. Frequency pattern is the center frequencies come in a pseudo-random pattern. Am I always guaranteed that the C over I in a frequency hopping system is better than a system that does not do frequency hopping? Am I always guaranteed that? So basically, is C over I improvement, is it guaranteed for every hop? Yes or no? The answer is no, because there may be another user who's using the same spectrum, and maybe somebody who's much closer to you. Therefore, there are some hops where you are going to have possibly worse C over I than in a system that you did not hop. But the most important thing to note is that you have improved the average C over I. On average, you will not get stuck with a bad interferer who is constantly bothering you. You'll average out the interferers, and therefore, of all the interferers in the system, if you could average your interference across them, it's going to be better than the worst case. So again, this is to take advantage of to remove the worst case interference scenario. And of course, we did mention it in the context of the introduction, that MIMO systems have multiple antennas at the base station and at the mobile, and those are techniques that we will exploit to use to do interference suppression. So again, that would help us improve the C2I calculations. Okay, now first example or task that I would like you to consider is a system which uses a one cell reuse pattern. So basically, I have taken the first tier of interferers, the 6 cells around it, and looked at the interference scenario. Basically, the interferers are all the base stations around you. Your target base station, my figure seems to have moved slightly offset. Assume that all the base stations are in the centers, and this red dot is at the vertex of that hexagon. So basically you have to compute the distances from each of the interfering base stations. Now let's take the first case. When you have the scenario of omni, all the base stations are going to interfere, 6 of them, B, C, D, E, F, G, C over I, if you calculate, basically it will be the sum of the interferences. So it would be R raised to the power minus 4 divided by 2 times R raised to the power minus 4. Notice that there are 2 base stations C and D which are at a distance of R from that. Plus there are 2 more terms which you would have to, which you can compute based on the geometry. But again, given that your desired signal is being overpowered by 2 interfering signals at the same distance, you expect your C over I to take a very significant hit, and which is what it does, minus 3.3 dB. And again, please go through the exercise. It's a useful illustrative exercise. Now, if I introduce 120-degree sectorization, so basically we'll assume that we're going to do 120-degree sectorization facing the eastward direction. So basically all of these base stations which are using the same frequency are going to be radiating in the eastward direction. So basically do the sectorization for all of them. Notice that C and D immediately are removed from the picture because they are radiating away from the mobile. But the remaining 4 are still present. But they are not at the same distance, so therefore you do see some advantage. You see that sectorization actually has bought you a lot for a n equal to 1 system, gives you 7.8 dB. If you did something clever to make sure that you could eliminate the B and E as well, maybe if the mobile moved in a little bit, something of that form, then C over I actually improves to 13.9 dB. So you can actually get fairly good signal to noise ratio provided you understand the impact of sectorization and of interference. Okay. Again, if there are any questions, let me know. I'm assuming these are fairly basic calculations. You'll be able to do them fairly easily. So the typical problem that you would encounter in a scenario like this, you would be given conditions such as hexagonal cells, omnidirectional, tier 1, maybe sometimes tier 1 and tier 2 are supposed to take, path loss exponent is given to you, and you want to calculate the cluster size, given that you have to satisfy a certain C over I condition. Again, this is already something that we have done. The purpose of this example is not to repeat that. So this calculation resulted in a cluster size of 12. Okay. Now, given that you're working in an environment where the channel will introduce a lot of errors, the introduction of error correcting codes or forward error correction or channel coding is very advantageous. So assume that you have introduced channel coding into your system, which means that you have to compress your source a little bit more. The little extra headroom that you have, you use it for error protection. But given that you have error protection, you're able to achieve the target performance at C over I of 9 dB. If that is possible, if you can design your error correcting codes to work at a target of 9 dB, then you redo the calculation. Basically go back and plug in saying that your target C over I is only 9 dB, and you find out that now we have a n equal to 7 as the new system. Now this is a correct way, a valid way of reducing the cluster size. So again, one of the ways you already have, one of the tools that you already have is the use of coding to achieve the desired reduction in the cluster size. And again, the benefits of reduction in cluster size, I don't have to tell you, you have already looked at it several times. Okay. Many ways of either reducing the interference or making the system more robust, all of these are come into picture when we want to design the entire system. Let's move on. Now I would like you to consider a real life example and basically put all the pieces that we have discussed so far. GSM uses 200 kilohertz channelization, okay? And the spectrum looks somewhat like what I have drawn. Basically the spectrum has a shape that has got a bump, and then there is a fall off, rapid fall off. So the neighboring channel, if I place it at 200 kilohertz spacing, you can see that there's a fair amount of overlap. That is your adjacent channel. Okay. Now, in GSM, it is customary that your receiver will have a receiver bandwidth of 180 kilohertz. I just want you to, why is it 180 kilohertz? Why not 200? What are the benefits? I want to reduce adjacent channel interference. I want to protect myself against adjacent channel interference. Okay. Now, what is the price that I pay? Loss of signal. Is that the only price? Is only the loss of signal? What happens to the noise? What noise going into the receiver? Because you have your signal and you have actually filtered your noise, so you get colored noise. Okay, coloration of the noise or coloration, the channel basically is introducing memory into the system. So which means that you have to have an equalizer. So this would basically mean that you would have to have an equalizer. Okay, you have gained in terms of the adjacent channel interference, but the price that you have paid is that your receiver will now become more complex. Now, why not make it 160? Because there you will start to lose more of the signal and you will have higher complexity, and by the way, reducing it to 160 may not buy you much in terms of adjacent channel. So keep that picture in mind, that there is one reason why we choose the receive filter. So the example that we now want to look at is, I have designed a system, I have basically laid out my system, and I find that I have achieved a certain range. But now the goal is, I want to improve the range, I want to increase the range. What are the tools that are available to me? What are the different ways? Very quickly, what are the ways in which I can improve the range? Transmit power, okay, I can increase transmit power. I would say it as EIRP, which means that you could increase transmit power, you could increase transmitter gain, you can reduce feeder losses, you can do many things. So basically transmit power can be raised, or EIRP. Effectively you can increase the EIRP. Okay, what else can I do? What do I do if I want to improve my receive signal power? RX signal power. If I want to increase my receive signal power, what are the ways in which I can do that? I have to increase my RX antenna gain, that is one way. I have to use a low noise figure. So I can reduce my noise figure. That will effectively give me a lower noise floor, which will give me an improvement in terms of that. Okay, and possibly I can think of the RX filter, and one way, but the reduction in the receive filter gives me a benefit is that if you remember, we do the PN calculation. PN is equal to KTB. That's the receive filter. So basically, by reducing the receive filter, I give a little bit of boost to my signal to noise ratio, because the bandwidth has come down, but I pay a price for that. So I would be very, very careful in terms of the introduction or changing the bandwidth of the receive filter, but that would be yet another way of doing that. And of course, frequency hopping to reduce the interference, but that wouldn't affect my range. So basically, range would mean that I have to either increase my signal or reduce my path losses. Again, path loss we don't have much control over, and so these would be some of the ways in which we would look at the task. Okay, so those are the three quick examples. We now move on to looking at signal quality. And I want you to start thinking along the lines of what we have studied so far and apply that. So let's first take a look at the noise limited case. Noise limited case, if I put a power meter after the receive filter, basically it will be signal plus whatever noise is present. So the received signal power is the signal power plus the noise power. Okay, whatever comes after the receive filter. So that would be my total received power. It will be signal component plus noise component. And in this, PN is fixed, because I know once I know the receiver bandwidth, I know PN is fixed. So if I find an increase, if I want to, if I find a way to increase my receive signal power, or for some reason my signal power goes up, then I'm very happy, because that tells me that's because my signal power went up, because the noise power has not changed. The noise power remains. So one of the metrics that we use in noise limited systems or in any wireless system is a measurement called the RSSI. I'm sure you would have come across the term. It stands for Received Signal Strength Indicator. Okay, so basically whatever is the received signal, you take its signal strength or you measure the power of the signal. It's a combination of signal plus noise. You know that the noise is fixed and therefore it gives you an estimate of how much signal is present. Now I want to move from there to a interference limited scenario. So in an interference limited scenario, if I do PR, I'm going to find PS. It will be a signal component, plus there will be a noise component, plus there is a interference component. So like before, Pn is fixed. I cannot do much about this. But Ps and Pi are things that can change because of the environment. Okay, so these are variable. So if I now look at a scenario where RSSI is increased through some mechanism, I find that I have received, should I immediately celebrate? No, because it could be signal or it could be interference. In both cases, I mean, in one case I am very fortunate, in another case I am actually quite unhappy. So this could be due to PS increasing or Pi increasing, that would also increase, or both. Now if both increase, doesn't help me because signal and power both have gone up, C over I has not changed. But if Pi goes up, I am really in trouble. Now how do I distinguish between these different scenarios? And for that, the only way we can do it is by looking at the bit error rate or the frame error rate. Okay, so there are certain fields in which we can do those measurements, and looking at that we get a metric called RX qual, received signal strength quality. Basically that tells you what is the bit error rate or frame error rate, and again different cellular systems will define it, but this basically will tell you that the signal is good or bad, which means that if RX qual is high, that means your signal to interference plus noise ratio is high. So RX qual is good implies SINR is good. Okay, so on one hand you have RSSI, then you have RX qual, and you have a combination of these two which are a very useful mechanism for us. So is everyone clear about the signal quality measurement in an interference limited environment and the interpretation of that? Because now we are going to try our understanding of this in a very, very interesting example. So I am doing measurements on my receiver. Okay, I have a scenario case 1 where RSSI is high and RX qual is also high. Okay, so what type of a channel is this? The scenario, if RSSI is high, that means I am probably close to my base station. So I'm interpreting this, so close to own base station, which is a good thing. If I'm close to my own base station, I'm far away from the interferers, so this is also a good scenario. So the assessment is that this is a good channel. Okay, very good. Keep the channel. Don't do anything. No action required. No change. Keep it as is. Okay. Second scenario, my RSSI is high. RSSI is high, and my C over I is low. Is that possible? Okay, give me a scenario that such a situation happens. If you are living in one of the tower hostels, basically you're on the 5th or 6th floor, you have a very good path to your channel, but you also have path to the interfering channels. So basically this is a situation where you are not far from your own base station, you are near own base BTS, okay, but there is high interference. Not a good situation. Do I need to change to another base station? No, because actually I am close to my base station. All I need to do is change my frequency. So this is a bad channel. I need to do an intra-cell handover to the same base station, but you ask for another resource, another frequency, because then you will see probably a better scenario. Okay. Now let's move to the third case. So the second case was a case where I am close to the base station, but I am seeing a lot of interference. Third scenario, RSSI is low. RSSI low means PS is low, PI is low, everything is low. So basically that means you are far from the base station. So basically we will call it as edge of cell. Edge of cell. Okay. Now your C over I is low. What does that tell you? You are closer to the interfering base station. So this is a scenario of high interference. But there is no point changing to another frequency within my own cell, because that is not going to help me. So this is a bad channel. So in this case I better ask for an inter-cell handover. Okay, I will go to another base station and maybe change because I am too far from my own base station. And then the last scenario, my RSSI is low. That means it is possibly edge of cell, and I have high C over I. What happened? Some magic? Can this channel happen?
Yeah.
Under what conditions?
Transmit power on other base stations are low.
So basically this says there is no interference, right, or interference is very low. So again, you are not happy because your own signal is not very strong, but this is a highly unlikely scenario, because this basically tells you that you are in a noise limited environment, because basically you are far away from your cell but you are still not seeing interference. That means the other base stations are not creating any interference or basically interference. So this is a unlikely scenario. In a cellular system that is heavily loaded, such a scenario rarely happens. So so very quickly you can look at it and say, unless both RSSI and RX call are high, you have to do something about it. So quickly look at which way you want to do and respond to the situation. That will help you handle the system. Okay, any questions?
What is the action if it has
Which one?
low RSSI, high RX call?
So what would you do? If it's a noise limited system, you are far away from your own base station, you would ask for handover, intercell handover. Yeah, intercell handover, but again, being a interference limited system, to say, oh, there's no interference is a sort of contradiction. But if you are fortunate to have that, then very good, just ask for an intercell handover and you'll to a closer base station. Okay, but it's a scenario that is probably somewhat unlikely to happen. Okay. Now this sets the stage for us to move into our discussion on the capacity of the system. We've now designed the system, we know cluster size, we know all of the elements that are associated with it. Now I want to understand the ability to work with these systems. Okay, trunking, the term that is used comes from the earlier telephone system. So basically this means that I have a large number of users, and there is a limited number of resources. Okay, so what I do is I pool my resources. Remember that ticket counter example. I treat the users as one large pool and I try to service them. So basically using the mechanism of pooling the users, pooling the resources, that way of thinking about it is the notion of trunking. In today's terminology, we don't use the notion of trunking. It is referred to as statistical multiplexing, and again we'll try to establish the link between the two. So our preliminary understanding of trunking says that the channels are in a common pool. All the channels in a common pool. Okay. Now when there is a demand for a channel that is assigned, so channels assigned on demand and then released once the requirement is end. Upon termination it goes back to the pool. Okay. Now what is it that the whole notion of trunking is? The whole notion of trunking says that all my users hopefully are not going to ask for resources at the same time. Okay, so that is the notion saying, okay, there are a large number of users and their usage patterns are similar, but hopefully they are not going to ask. So the notion that not everybody is going to ask for the same at the same time. So basically we want to exploit statistical behavior of the traffic. Okay. Now we use this notion of statistical multiplexing very heavily in internet traffic, because we have a large number of users who are connected to the internet, and we want each of them may ask for download of a large file, but the statistical multiplexing says is as long as they all don't ask for it, each of them will see a good data rate. So basically exploit statistical nature or statistical behavior. It can be behavior if you talk about the user, statistical nature when you talk about the traffic. So basically this is the notion of these system. Okay, now let me just define the context and then we move forward quickly. So we have a cellular system which fits into this mechanism, large number of users, limited number of resources. Now typically in this type of scenario, when a user is asking for resources, if the resources are available, the user will be served. Either you are served or you are blocked, or the third scenario is that you are queued. You are in a line waiting for the service to happen. Served means the resources were available, you are readily given. Blocks means you are said no, come back at a later time. This means wait. Okay. Now is the cellular system a queued system or is it a blocked system, a system that does blocking or queuing? Blocking. But what about call waiting? Isn't that what queuing is supposed to be? Say wait till, think about it.
But resources have been allocated to that user.
Excellent point. The resource has already been given to you. So basically you are not blocked. The only reason the call did not complete is because the user was not. So call waiting is not a queuing system. So call waiting is not the same as queuing. Okay, our system that we have for cellular is a system that will block. If it does not have resources, it will block the user. Okay. Keep that picture in mind. Let's just quickly define our measure of capacity and develop a quick intuition for the system. Okay. Now this goes back to circuit switched context. We will discuss our capacity using a circuit switch context, but the principles that we learn are very much valid for the packet switched context also, and so the tools are very relevant. So keep in mind. Basically this comes from the PSTN era, where all of our networks were switched landline telephone networks, and a Danish engineer by the name Erlang actually did the capacity calculations, and that's why we call it as the Erlang formula or the Erlang when you talk about traffic. So the first point that I want to make is that the definition of one Erlang, which is basically our fundamental unit of traffic. One Erlang implies one channel that is fully utilized. One channel which is fully utilized. That means there is no idle time for this particular channel. Okay? So basically if you think of your unit of time as 1 hour, you have basically used this channel for 1 call hour. That means the entire hour the call was on for an hour, per hour. 1 call hour per hour means there is no idle time, the channel has been fully utilized. So let's make a quick example for this and then build on that. Supposing I have a user. This user makes 1 call every hour, 1 call per hour, and the duration of the call is 10 minutes. Duration equal to 10 minutes. So now if I look at it, the utilization is 10 minutes out of 60 minutes. So basically it's 1/6 of an Erlang is what this user has, is the traffic that this user has provided. He didn't provide 1 Erlang. Again, one user cannot provide more than 1 Erlang, that's the upper limit. Most of the time you give something less than 1 Erlang. So now the question that arises is, I have 1 channel which can carry the traffic of 1 Erlang, and I have user which generates 1/6 Erlang, can I say I can now support 6 users? So 6 users question mark implies 6 users question mark. The answer is yes and no. Yes, if all of them are perfectly multiplexed statistically. When one finishes, somebody else starts using the channel. But if they are random users, they basically will make their calls, this will not work. Basically, this is a scenario that will end up being in a lot of block situations. So that is the problem that Erlang analyzed. Now, given a particular number of channels, given a certain number of traffic that is being generated by these users, how much statistical multiplexing can I assume, therefore, to give reasonable amounts of performance? So the probability of blocking is that when a particular user asks for a channel, the channel is not available. So probability of of a user getting blocked now will become a percentage. What is the probability? Is it a 2% probability or a 3% probability? So usually, typically, it's in the 2 to 3% is probability of blocking. This is what we refer to as grade of service. In the landline system, you are supposed to have guaranteed service, so even a 1% grade of service was sometimes considered as not good enough. But in a cellular system, sometimes we are very happy if we can do 5% grade of service, because there are times when there are peak hours. So typically the blocking probability of grade of service has to be measured during peak hour. And there are certain scenarios, like for example, if let us say there has been a train accident, then of course the system will get completely jammed because everybody is trying to make a call. Those are exception situations. But under normal conditions, if you have peak traffic, that is under that conditions, what is the blocking probability, and that is what we are going to be measuring. So now very quickly, let us put into place the mechanism for measuring the grade of service or the blocking probability. So here are the basic parameters that Erlang had used in his analysis. So there is a certain call arrival rate. And this is, let's call it as lambda. Lambda calls per unit time per user. Okay, so this could be, for example, 2 calls per hour per user, or something if my unit time is per hour, or 1 call per 10 minutes. Whatever is your unit of time, basically this is the arrival rate. The average duration of a call. Average duration of a call, that's called the holding time. That's the time for which you are using the channel or holding the channel. Let's call this is called holding time, or H. And whatever is your unit time, you should use the same unit here as well. If you used minutes, use minutes here also. This is holding time, and that is denoted as H. Now the traffic intensity per user, or the traffic offered per user. So basically the traffic per user is AU. A stands for traffic, a subscript U is the per user, will be lambda calls per unit time, and each time you are going to hold the channel for lambda H. So basically, if it's 2 calls for 10 minutes, that's your loading onto the channel. So lambda H gives you the traffic. And if the total number of users in your cell, total number of users is equal to U, then the total traffic within the cell, total traffic within the cell, total traffic in the cell will be AU times, that is per user, times U, the number of users. There is an important distinction that is made. This is called the offered traffic. That means this is the traffic that the users are offering to the system. Now if it is 2% blocking, then you would have to multiply this by 0.98 to get the carried traffic. That is what the system actually carries. So there's a difference between what the users offer and what the system carries. It's not exact because of the blocking probability. We also make the following assumption that there are number of channels available to us, number of channels equal to C, and this basically leads us to the most important parameter, traffic intensity per channel. Traffic intensity per channel. Okay, that is the key metric that in our discussion, that will be A divided by C. Now, as you can see, the more for a given traffic, if I keep increasing my number of channels, obviously blocking probability should reduce, because that's the basic understanding, that the more resources are available, and eventually if I have as many channels as number of users, there will not be any blocking. But the idea is not to reach that point, just to find out what is that number that will give you good grade of service without asking for the number of channels equal to number of users. So that was the primary contribution of Erlang. So now, given this framework, we would now jump ahead and give you the result that Erlang had derived, and here are the basic assumptions. The basic assumptions are that I have a system that has C channels, and these C channels are being offered a certain amount of traffic, and this traffic, the desire is to find out what is the blocking probability of this system. And so the formula that Erlang had derived is that the probability of blocking Now, this assumptions of probability is based on a certain mechanism that is arrived. Basically, he said that we will assume that there are the arrivals, the rate at which the calls are coming in are memoryless. So, memoryless arrivals. That is the first assumption. So, it does not matter, you do not make any assumption about who else has made a call or not. So, that is the first assumption. So, memoryless arrivals. Second one is that memoryless service. So, this also tells us that how much time you hold the call does not get affected by how much time somebody else is holding the call. So, what was the assumption that he made? That the duration of the call is exponentially distributed. Duration of call is exponentially distributed. What that means is that this is, if you call this as the probability of H, and this is H holding time, this probability actually is a decaying exponential. The likelihood of very long calls is less than shorter calls. That was the assumption that Erlang made. Maybe not valid anymore because people do talk for long amounts of time, but at least his assumption was that the shorter calls were more likely to happen, and most important, that there is a finite number of channels. Finite number of channels. So, in the notation of queuing theory, which many of you will be familiar, this would be called as an MM queuing system, memoryless arrivals, memoryless holding time. Then there are C channels and C users. It should be C is the number of channels and C is the number of simultaneous users. Let me just clarify that. This is the number of simultaneous users that you can support. Okay, the number of users is much larger. The number of simultaneous users you can support. So, in other words, why am I? Isn't it obvious that C and C are the same? In some systems, which we will talk about, if you have C channels, you may reserve 1 or 2 channels for emergency use, and therefore it will be C minus 2 or C minus 1. So, the number of simultaneous users can be less than the number of channels available if you have to put any restrictions on the usage of the channel. So, memoryless arrivals, memoryless service, C channels and max number of simultaneous users is also given to us. So according to this, the blocking probability derived by Erlang is a power c divided by c factorial divided by summation k equal to 0 through c, the uppercase is the number of channels, a power k by k factorial. Okay. Now, this is a result that we would like to use because our intention is not to prove Erlang's his hypothesis, but to know that it has been verified in circuit switch systems, and therefore our interest is to understand the traffic. So basically, assuming that the blocking probability is given by this is a formula that you will have studied it as Erlang B, Erlang formula for blocking. There's another formula called Erlang C for queuing. Again, ours is not a queuing system, so therefore we deal exclusively with the Erlang B. I won't even mention the Erlang C part of it. Okay. Now, what I would like to do is look a little bit closer at Erlang's contribution, because there's some very, very valuable observations, and so basically quickly write down, this is memoryless arrivals, memoryless holding time, this is the number of channels, this is the number of simultaneous users. Okay, so please be clear on the notation that is being used, and the blocking probability formula we have already written. I won't do that. So basically, Erlang calculated these blocking probabilities and drew them in the form of graphs. The y-axis is blocking probability. Okay, that's grade of service. So this you could also label it as grade of service. Grade of service, and on this axis is Erlang's. So eventually, all the systems, as traffic keeps increasing, doesn't matter, eventually you will get to blocking probability of 1. Once the traffic reaches a certain level, you will reach, so there is a upper limit of blocking probability of 1. But that's not the range of interest. Most of the time the range of interest is around 1% blocking probability. So notice that it is a system that is plotted logarithmically on a log scale on the y-axis. It's also log on the x-axis. Notice this is 1, 10, 100. That's the offered traffic in Erlang's. Each of these graphs corresponds to a certain number of channels. This says 2 channels. The print is a little bit small, but hopefully you can see it on the figures that you have on the phone. So if I have 2 channels and I want to have a blocking probability of 1%, then I look 1% line, then I map it down, and then I tell you, okay, the traffic has to be 0.17 Erlangs. That's all I can carry if I have only 2 channels. So basically, this is a very useful chart. However, keep in mind, these are very steep graphs, so you have to get your readings fairly accurate. Don't do gross approximation, because then you will go, your answers will be quite inaccurate. So let us quickly apply this. Let's take a couple of examples and apply it. Again, I'm assuming these are very straightforward for you to do, but it's good as an exercise. Supposing I have C equal to 5 channels, okay, and I have A as 1.36 Erlangs, the total offered traffic. I want to know what is the blocking probability. Probability of blocking. So this is not a graph problem, it is a problem for which you have to do the calculation. So basically, a power c divided by c factorial divided by summation k equal to 0 through 5 a power k by k factorial. And it's not difficult, just actually do the calculation. You will find that this comes out to be approximately 1%. It's a good system. For a traffic of 1.3 Erlangs, if I have 5 channels, then I get a blocking probability of approximately 1%. That's a good design. Okay, so basically, please go through and calculate this example. That will be a useful exercise. Now here come the variations of this particular example, which are very, very helpful for us. So we have the reference point. If I have 5 channels and a traffic of 1.36, I will get a blocking grade of service or blocking probability of 1%. And this corresponds to a traffic intensity. Traffic intensity would be A by C. A by C of 0.27, 0.27. Okay, that's the traffic intensity that I have. Now, if I go to 10 channels and I still want to have 1% blocking probability, I go to the graphs, get the 1% blocking probability, and I find that this corresponds to 4.46 Erlangs can be carried. So basically this is 0.446 is the traffic intensity. Notice that now I'm able to put a lot more traffic intensity onto my system. With 10 channels I'm able to support a lot more traffic. So keep in mind that because of the non-linear relationship between the number of channels. Okay. Now very quickly let us try some, I would like you to try out some of the other examples, 20, 40, and maybe jump all the way to 100. Please fill in the intermediate values. You will find that for a 1% blocking probability with 100 channels, you can support 84 users. So which means that the loading or the traffic intensity that you can carry is almost 0.84. That means your channels will be heavily utilized. And the more they are utilized, that means you are able to carry more traffic. So this is a very good scenario for us to have. Okay, so keep in mind that it's a non-linear relationship. There is a huge advantage when you have more number of channels. This is what we refer to as trunking efficiency. Okay, now if you remember, we said don't do too much of sectorization because you will lose trunking efficiency. Probably now it becomes clear, because if my channel originally had 60 channels, my cell had 60 channels, I divided into 3 sectors, each of them will become 20. And notice that it's a non-linear relationship. The net traffic that I now will carry in the same cell for the same 60 channels will be less than if I had a single cell of 60 users, 60 channels. So again, that's the trunking efficiency. Let's look at this particular result from a slightly different angle. Let me fix the number of channels as 5. If the offered traffic is 1.36 Erlangs, I know that I will achieve a grade of service of 1%. Increase this slightly, 2 Erlangs, the blocking probability jumps up to 4%. Go to 2.9, this goes to 10%. So notice that you are nowhere close to the channel and the number of channels, it's only 2.9, but there is a non-linear growth of the blocking probability. So again, so this is on the one direction. What happens if I reduce, if I go down from 1.36 where I have 1% blocking probability to 1 Erlang, it goes down to 0.3%, and then just a slight reduction beyond that goes down to 0.1%. Okay? So there are huge advantages to keeping a large number of channels in the pool, because that's when you get the trunking efficiency. So trunking efficiency, very, very important. This is leveraging what we know as statistical multiplexing. Okay? Any questions? Hopefully this gives you a very good handle on understanding why we said don't do too much sectorization, or try to make your cluster size as small as possible so that you can get as many channels in each cell as possible. So those are the thinking behind and what we are asked to. Okay, let me close with one more very simple example. So this is a situation where my target grade of service is 1%. Okay? And if you were to draw go look at the graphs, there are 2 scenarios. I have each user generates 100 milli Erlangs. That is the same as 0.1 Erlang. 0.1 Erlang, or in other words 1/10th of a call hour per hour. Okay, you can interpret this as each user makes one call basically for 1/10 of the hour, that's maybe 6 minutes, and that's all the user makes. So this is the traffic per user. Okay. Now I have two scenarios. I have one scenario where I have 10 channels and another scenario where I have 20 channels. I have to satisfy the same grade of service, and in each of those cases I want to know how many users I can support. So basically I go to the graph, the blocking probability versus Erlang traffic. This is the Erlang B graphs. I take the 1% line, take for C equal to 10, I drop the x-axis. I know that is the total traffic that I can carry with 10 channels with a blocking probability of 1%. So that comes out to be 4 Erlangs. So for this case, the A10 corresponds to 4 Erlangs, 10 channels, blocking probability of 1. So the number of users I can support will be 4 Erlangs divided by 0.1, because that's the number of Erlangs per user. So this tells me that we can support a total of 40 users in the system. Okay. Now I double the number of channels, and I find that A20 again from the graph, not done anything, no calculations, is 10.1 Erlangs. So this would imply that I would satisfy 101 users. So doubling the capacity of number of channels more than doubles the number of users that I can. This is another way of visualizing the trunking efficiency of the system. Okay, now maybe just to get you thinking about the case study, let me just give you the data and then we will pick it up from there. A city with a population of 2 million. Each user makes 2 calls per hour, 3 minutes per call. So this is the traffic per user will be 3 times 2 divided by 60. So basically this is the same case as what we had previously. 0.1 Erlang is mine. I want to have a grade of service of 2%. Now operator A has designed the full system, has made 394 cells to cover the system, and is getting 19 channels per cell. Operator B is created a coverage with 98 cells. Basically all of them have covered, they all have met the 2% grade of service, and he has 57 channels per cell. And then the third one is operator C. He has created 49 cells, he has created 100 channels per cell and has covered the service. Okay. Now what is the strategy of operator A, B and C? Okay. Obviously they have designed it very differently. Some of them will have a large cluster size, some of them have got large cell size, somebody has got small, somebody has optimized for cost, somebody has optimized for capacity. So take a look at it and try to see if you can get a feel for A, B and C, who is the smartest of these 3 operators, and if you had to do it, which way you would do it. So something for us to think about. Okay. Any questions on this problem? Basically this is a problem I would like you to think about, and then we will discuss it in detail at the starting of next lecture. Okay, thank you.